Start with a big picture idea, knowledge representation. One of the long-standing goals in artificial intelligence AI is to represent human knowledge in a way that machines can use. We want computers to not just store data, but understand and reason about it. One common approach to knowledge representation is RDF, which stands for Resource Description Framework. RDF is used to represent facts in a very simple format known as triples. A triple consists of three parts: subject, who or what we're talking about; predicate, the property or relationship we're describing; object, the value or target related to the subject. Here's an example: NBA minus 2019 winner Raptors. This means the winner of NBA 2019 was the Raptors. It's easy to break down, right? Let's try another one. Washington, D.C., capital of USA. This triple says that Washington, D.C. is the capital of the USA. It's clear and straightforward, almost like a sentence in English. RDF also helps to model objects and relationships, similar to ER entity relationship models, but more flexible. For instance, we can describe an entity like a person, John Doe, age 30, and the relationships between two entities. John Doe lives in New York. RDF is very versatile because you can add or modify facts without breaking the structure. And it's naturally represented as a graph, which leads us to our next slide. Now let's see what RDF triples look like when we visualize them as a graph. In this graph, the subject and object are the nodes or points, and the predicate is the edge or line connecting them. So each triple becomes a small piece of the graph. Imagine we have these triples: NBA 2019 winner Raptors, Washington, D.C., capital of USA, Washington, D.C., population 6,200,000. If we draw these triples as a graph, NBA 2019 will have an arrow pointing to Raptors labeled winner. Washington, D.C. will have an arrow pointing to USA labeled capital of. Washington, D.C. will also have another arrow pointing to 6,200,000 labeled population. What's cool about this graph representation is that you can add new facts by simply connecting more nodes. For instance, if we learn that New York City has a population of 8.4 million, we can add it to our graph without changing anything else. These knowledge graphs can grow and evolve as new information comes in. Let's take another look at RDF triples, but this time we'll break it down into even simpler terms. Each RDF triple is made up of three parts. Subject: this is the thing we're talking about, like a person or city. Predicate: this describes a characteristic or relationship like age or lives in. Object: this is the value or entity that the subject is related to. For example, Barack Obama, president of USA. Here, Barack Obama is the subject, president of is the predicate, and USA is the object. Think of it as a sentence with three parts, just like this one. Barack Obama is the president of the USA. Let's try a couple more. Apple, founded by Steve Jobs. Amazon, CEO, Jeff Bezos. These triples are simple but very powerful because they can represent just about any fact in the world. Now that we know how to represent knowledge with RDF triples, the next question is, how to retrieve information from these triples? The answer is SparkQL, a special query language for RDF. Imagine you want to find the names of students taking a course called Intro to Computer Science. With SparkQL, you can write a query like this: select, name, where, SciD title Intro to Computer Science. SID course, SciD takes, SID ID name, name, what. Does this mean? Let's break it down. SID stands for the course ID. SID stands for the student's course ID. ID stands for the student's ID. Name stands for the student's name. We're asking SparkQL to return the names of all students taking the Intro to Computer Science course. This is similar to SQL. But instead of dealing with rows and tables, we're dealing with triples and relationships. Another important feature of SparkQL is that it supports advanced queries like aggregation, count how many students are in a course, optional joins, fetch data even when some parts are missing, subqueries, run a query within a query. SparkQL makes it possible to dig deep into these knowledge graphs and get the information we need in a structured way. One last point about RDF. We've talked about how RDF triples represent binary relationships, which means they can only connect two entities at a time. But what if we need to represent more complex relationships, like multiple things happening at once? For example, how would we represent the fact that Barack Obama was president of the USA from 2008 to 2016? A simple triple can't hold all this information. One way to do it is by creating an artificial entity like this: E1 person Barack Obama, E1 president of USA, E1 president from 2008, E1 president till 2016. Here, E1 is a new entity that acts like a container for all this information. This is useful when you have multiple facts that need to be tied together. Alternatively, we can use quads instead of triples. Quads add a fourth piece of information called the context entity to store additional details. This helps us keep everything organized and structured. RDF is widely used in various knowledge bases like DBpedia, Yago, Freebase, and Wikidata. These are databases filled with RDF triples that store millions of facts about the world. They are part of the Linked Open Data project, which aims to connect different knowledge graphs together. Next, let's move on to how object orientation fits into databases. Many applications today are written using object-oriented programming languages like Java or Python. However, the relational model used in databases doesn't match the object-oriented world. This mismatch causes problems, especially when switching between writing imperative code like in Java and querying data using SQL. There are a few ways we can deal with this. 1. Object relational databases. These databases add object-oriented features to relational databases. They allow us to work with complex data types and include object orientation. 2. Object relational mapping, ORM. This is a process where we automatically convert data between object-oriented programming models and relational databases. 4. Example, in Java, we can use ORM libraries like Hibernate to manage this conversion, while Django handles this in Python. Let's say you have a person object in your code. With ORM, this object can be mapped to a table in the database. And when you make changes to the person object in your code, the corresponding database rows are automatically updated. Let's look deeper into object relational database systems. In an object relational system, we can define user-defined types to represent more complex objects. For example, create type person as ID varchar 20 primary key, name varchar, address varchar 20. We can then use this type to create a table. Create table people of person. This means we can now insert, update, and query person objects as rows in the people table. Another example, let's say you want to store a user's interests as a list of topics. You can define an array or multiset type to store this information. For example, create type interest as table, topic varchar, degree of interest int, create table users, ID varchar name varchar interest. These advanced features help bridge the gap between object-oriented programming and relational databases, making it easier to handle complex data in a flexible way. Another cool feature of object relational databases is inheritance. Just like in programming, you can have one type or table inherit from another. For example, let's say we have a person type, And we want to create subtypes for students and teachers. Create type student under person. Degree Varchar 20. Create type teacher under person. Salary. This allows us to extend the person type with additional attributes specific to students or teachers. Similarly, we can use table inheritance to create tables for students and teachers that inherit from the people table. For example, in PostgreSQL, we can write create table students, degree Varchar 20. Inherits people now, the students table will include all the columns from the people table, plus any additional columns specific to students. This is a powerful way to model complex hierarchies in your database. Let's wrap up this section by talking about reference types. In an object relational database, we can create references between different types. For example, we can define a department type that references the person type for its head. Create type department as dep name Varchar, head ref person scope people. Create table departments of department. This allows us to create a reference from the department table to the person table. We can insert data like this. Insert into department's value sees here 12,345 feet is the id of the person who is the head of the department. We can even retrieve these references using path expressions. For example, select head greater than name, head greater than address from departments. This query will return the name and address of the person who is the head of each department. Reference types make it easier to model relationships between different entities in your database, similar to how we use foreign keys in traditional relational databases. Let's talk about object relational mapping, ORM, which is a very useful concept when working with databases and object-oriented programming languages. ORM allows us to map objects in our code to rows in a database. This means that when we create an object in a programming language like Python or Java, ORM systems will automatically handle saving that object in the database and even updating or deleting it when needed. For example, if you have a user object in Python, the ORM system can automatically generate the corresponding SQL commands to insert or update that user in the database. This makes development faster and easier because you don't have to manually write SQL queries. Here's how this Let's shift gears now and talk about textual data. When we're working with text data, whether it's emails, web pages, or books, it's usually unstructured. Unlike the structured data we store in databases, unstructured textual data doesn't fit neatly into tables. This poses a challenge when we need to search through and retrieve meaningful information from large amounts of text. One of the simplest models for working with textual data is keyword querying. Let's say you want to search for the word cricket in a large collection of documents. A keyword query would return all the documents that contain the word cricket, but that's just a starting point. We also want to rank the documents so that the most relevant ones appear first. For example, if one document mentions cricket 50 times, it's probably more relevant than a document that only mentions it once. To handle this, we use something called TF-IDF, or term frequency inverse document frequency. Here's how it works. Term frequency TF measures how often a term appears in a document. The more often it appears, the more relevant that document is. Inverse document frequency IDF measures how common or rare a term is across all documents. Rare terms get a higher weight because they are more meaningful. For example, in a collection of sports articles, the word cricket might have a high TF-IDF score in documents that discuss cricket, but a low score in documents that mention cricket only briefly. This helps us rank documents based on relevance. Now let's talk about how we rank web pages using hyperlinks. This is one of the key techniques behind Google's PageRank algorithm. Here's the basic idea. Web pages that are linked to by many other pages are probably more important or relevant. So a page with many incoming links from other pages should have a higher rank. Not all links are equal, though. If a page is linked to by highly ranked pages, that link is more valuable than a link from a less important page. We can formalize this idea using a random walk model. Imagine a random person clicking on links across the internet. The probability that they end up on a certain page depends on how many other pages link to it. This is captured in the PageRank formula. PH equal to delta in 1 delta sigma t JP, where pj is the PageRank of page j tie j, is the probability that a random surfer on page I clicks a link to page j. Delta is a damping factor, which is usually set to 0.15. N is the total number of pages. The formula is iterative, meaning that we keep updating the ranks of pages until the values converge. The end result is that highly ranked pages, those with many high-quality links, will rise to the top of search results. This algorithm revolutionized how search engines rank pages and is still in use today, although modern ranking algorithms use many more factors in addition to PageRank. When it comes to searching large collections of documents, we want to measure how well our search engine is performing. Two important measures of retrieval effectiveness are precision and recall. Precision tells us what percentage of the documents returned by a search are actually relevant. In other words, if we retrieve 10 documents and 7 of them are relevant, we have 70% precision. Recall tells us what percentage of the relevant documents in the whole collection were actually returned by the search. If there are 100 relevant documents in total, and our search retrieves 70 of them, we have 70% recall. Both of these measures are important, but there's often a trade-off between the two. For example, if you want to maximize recall, you might end up with lower precision because you're retrieving more irrelevant documents. In real-world applications, we often use measures like Precision 10 or Recall 10, which tell us how well the system performs when limited to the top 10 search results. This is especially useful when users are only likely to look at the first page of results, like on Google. Now let's turn to a different kind of data, spatial data. Spatial data is all about location. This includes things like geographic data, road maps, land use maps, political boundaries, etc. Geometric data, design information, like the layout of a building or the components of an integrated circuit. Spatial databases are designed to store and query this kind of data efficiently. One example of a spatial database is a Geographic Information System, GIS, which stores and analyzes geographic data. Spatial data is often represented using a coordinate system, like latitude and longitude for geographic data, or XYZ coordinates for geometric data. For example, a line segment can be represented by the coordinates of its two endpoints like this, line string 1, 1, 2, 3. Spatial queries are a bit different from traditional database queries. Instead of asking for a specific row or column, you might ask for all the objects within a certain region, or find the object nearest to a given point. Spatial databases also support operations like scontains, finds all objects contained within a region. Stintersection finds the intersection of two regions. These types of queries are incredibly important for applications like mapping, navigation systems, or even video games, where spatial relationships are crucial.